It's recording, and for now, I'll give the floor to Tom and wishing you all a good workshop. Thank you.
Thanks, Rita. Good morning, everyone. If you just bear with me a moment, I will share the slides to run through today. So let's get this up. Hopefully, everyone can see that okay. I assume that's the case, so I will crack on.
Yeah.
Good morning, everyone. My name's Tom Andrews. I'm an advanced research engineer in the material science team at the NCC, based in Bristol, in the UK. So today we're going to talk to you about some of the results from the GreenLoop project, specifically looking at the biorubber value chain that we've been developing. So this is the agenda for today. I'll spend a couple of minutes talking about GreenLoop as a whole, and then a few minutes on the biorubber value chain specifically. I'll keep that as short as possible to allow us as much time to disseminate some of the technical results. So some of my colleagues, Hassam, will be talking about the work University of Bristol have been doing on the chemical devulcanization, and then also producing some multi-layered rubber paneling. Then Professor Fabrizio Scarpa, also from Bristol, will run you through some of the vibrational testing results. And finally, Frederic from ZAG in Slovenia will be talking about the fire testing results. And hopefully, if we keep to time, that leaves a decent amount of time for Q&A at the end. So I'll dive into it then. The GreenLoop project as a whole, it's a Horizon Europe project, 3-year project that kicked off in September 22. So we're coming right to the end of the project now, and we'll finalize next month in August. And I suppose the overall aim, the mission for the project itself was to develop bio-based value chains and taking them up from TRL 4 through to TRL 6 at this point, really at the end of the project. There was 3 of those value chains. So the first is the biorubber, which we're going to talk about today. So that's generating anti-vibration paneling for use in construction. Alongside that, there's a value chain looking at bioplastics and specifically bio-derived thermoplastics for use in bottle closures for the food industry. And then the third one was wood thermoplastic composites to be used in bearing applications. So those are the 3 value chains. I guess underpinning that then there's the approach that we've taken, which is really to be thinking about the circular economy potential of these products from the R&D stage. So we're thinking about how do we sustainably source the raw materials, how can the products be reused, refurbished, repaired during their life, and then if they do reach their end of life, how can they be recycled? And then underpinning that work, there's some enabling technologies, I suppose. So there's been work carried out looking at how AI can help the R&D process. So predicting material properties and processing parameters and guiding some of the research. There's also been work looking at novel heating techniques for some of these processes. So in the biorubbers case, is actually looking at utilizing ultrasound for the devulcanization and combining it with green chemistry principles. Sam's going to talk about that in a little bit. But for the other value chains, it's been using microwaves or microwave technology to heat material during extrusion of the polymer. And then finally, a digital platform is being built at the moment, which will be publicly accessible, and all the results and actually some of the models that have been developed will be on that platform, just to make sure that this project is as open as we possibly can be, and shout about the results that we've generated. So that's GreenLoop as a whole then. I've just got a couple of slides on the biorubber specifically. So to simplify it right down, and this really is a simplification, the 2 main components that go into our formulation is rubber. That rubber is sourced from ground tire waste. So there's actually a mix of synthetic and biorubber. I know the value chain is called biorubber value chain. Maybe it's more accurate to say it's bio and recycled rubber. We then combine that with lignin, so compound it and then press it into rubber paneling. The reason for looking at lignin is it has an impact on some of the mechanical properties, but also interested in its ability to modify the panel's reaction to fire, although Frédéric will go through some of those results later on. And I suppose, why are we doing it? Well, essentially we're targeting materials that are readily available. There's an awful lot of waste of both rubber and biomass generated well globally, but got statistics for Europe here. And I suppose really what we're trying to do is work out how we can keep their value and keep them within the circular economy. And then I guess just to emphasize what we're doing here, there are a lot of recycled rubber panels on the market. Most of them use the rubber as a filler. It produces a good product, but often that filler is bound together with a virgin fossil derived resin, and that also makes them pretty hard to recycle, because you've essentially then got a composite material. So we're trying to produce panels that then theoretically can go back through that recycling process and are used again. So this is my final slide, but this is broadly the process that we're going through. So we're taking devulcanized rubber, so rubber where the cross-linking bonds that have been formed during its first processing, they've been broken, so you can reprocess that rubber. We compound it with lignin extracted from waste biomass. So that lignin extraction has been carried out by one of the partners, NIC, who are based in Slovenia. The compounding and formulation work, that's been a collaboration between ourselves at the NCC and the University of Bristol. That then comes to us at the NCC. We compression mold it into panels, and we've kind of scaled up all the way up to about 0.5 meter by 0.5 meter panels. Sometimes that's the final part. Sometimes there's a coating application either at Bristol or ZAG. And then those final parts, they go through testing, essentially. So vibrational testing at the University of Bristol, mechanical testing at ISQ in Portugal, and fire testing at ZAG in Slovenia. So that's the critical path. We've been using some commercially available devulcanized rubber. Alongside that, we have been exploring other ways to perform that devulcanization, and that's been a collaboration between the University of Bristol and IRIS, who are based in Barcelona. So that's everything I will say as an introduction. I'm going to pass over now to Hissam, who is going to run through some of the chemical devulcanization work and also some of the coating work. Hissam, the floor is yours.
Thank you very much, Tom. Hello, everyone, and good morning. My name is Hissam Ramazani. I am a research associate at the University of Bristol, Bristol Composites Institute. My presentation starts with the devulcanization of chrome rubber using deep eutectic solvents. Deep eutectic solvents are basically a combination of 2 or 3 hydrogen bond acceptor and hydrogen bond donors, as you can see in the figure on the right-hand side. This enables these materials to form hydrogen bonds between each other, which makes them a very flexible compound to work with. And as a result of that, they can be synthesized very simply by mixing them in powder form and heating them up to low temperatures. In our case, we use choline chloride with a melting point of 300 degrees and urea with a melting point of 130. But after mixing them in powder form, they turn into an odorless and clear solvent at 80 degrees. And the solution is also very stable. So this is the solution that we use alongside low power output sonication, ultrasonication, to devulcanize the chrome rubber. Next, please. Here you can see the trials of the devulcanization. We used 4 different chrome sizes, the tire rubber that Tom mentioned, and the sizes ranged from 0.6 millimeter to somewhere around 0.12 millimeters. And the highest percentage that we achieved was 58.13 for the smallest size of chrome rubber. But during devulcanization, there is also the potential to break the backbone of the polymer, which is basically considered as the degradation of polymer. In order to evaluate that, we use Horrocks formulation and equations. And as you can see on the Sol fraction devulcanization plot, there is a red curve, and the region below the red curve belongs to selective crosslink scission, where the crosslinks or the sulfur bonds that hold the rubber chains together are located. And in that region, if the calculations show we are there, we are basically selectively cleaving and breaking the crosslinks. Next, please. To confirm the results, we used SEM and AFM microscopy. As you can see in the left-hand side SEM image, the surface of the rubber is plasticized and looks molten, which shows that the devulcanization has actually affected the rubber crumb. And on the right-hand side, on top, we have the AFM images of untreated rubber. As you can see, the surface is very rough, while the below image, which is after devulcanization, shows a smooth surface. And actually, the average adhesive force was 5 times greater than that of the untreated rubber, which shows that the surface of the rubber was very sticky after devulcanization. Next, please. For the next step in our research, we tried to find some application for the recycled rubbers, and we came up with the idea of a novel class of multi-layered coated recycled rubbers. So in the schematic, you can see that we have multiple rubber layers. These are recycled rubber layers that are coated using biodegradable and water-based coating based on lignin, cepiolite, and polyacrylic acid. These layers are coated on one side, stacked on top of each other, and then hot pressed at elevated temperatures to manufacture the final part. In the images, you can see the steps. So on top, we have the coating stage. Then you can see the dried rubber sheets after coating and the final part. And below, you can see the flexibility and also the dimensional stability of the part. Next, please. To evaluate the performance of these rubbers, we performed a series of tests, and you can see the results of the monotonic and cyclic compression tests. So here we have the monotonic compression test, and as you can see from the stress-strain plot, the multi-layered rubber have a better performance in terms of compressional strength compared to the unlayered sample, and also a higher modulus. In the next slide, you can see the cyclic compression test results in which the multi-layered samples show more hysteresis. The hysteresis is the area inside the loops, as you can see, and also a higher stored energy, higher dissipated energy, and also modulus. I need to mention that the 3-layered sample has a better performance in terms of monotonic and cyclic compression compared to the other 2 samples. Next slide, please. To evaluate the impact and acoustic properties of the rubbers, we performed other tests. And as you can see on the left-hand side, we have the specific energy absorption versus nominal strain and nominal stress versus nominal strain. So between 10 joules and 40 joules of impact energy, basically every sample had the same performance. But it gets interesting when we reach the 50 joules. And as you can see, the 4-layered sample shows a higher capacity for absorbing the energy and for dissipating it through different mechanisms. And we also see that for the unlayered sample, after the 40 joules, the nominal strain is limited to nearly 50%, while for the 3-layered is 60%, and the 4-layer is nearly 70%, which shows that the multi-layer samples are more compliant. And they can be used in the applications that needs compliant materials. And finally, the acoustic properties is completely different because here the unlayered sample has the better performance in terms of dynamic storage modulus, dynamic loss factor, and as a result, a higher dynamic loss modulus. This shows that depending on the design of the material and on the type of the coating that we are using, we can use these recycled rubbers and coated rubbers in various applications. This concludes my presentation. Thank you very much, and I'm looking forward to any questions that you guys have. I'll hand over to you, Tom. Thank you.
Thanks very much, Hassam. I think probably it's best we'll leave questions till the end, so we'll move on now. Fabrizio Scarpa from the University of Bristol as well is going to talk to us about some of the further vibrational testing they have carried out. Over to you, Fabrizio.
Thank you, Tom. My name is Fabrizio Scarpa from the University of Bristol. I'm a Mattias team leader for the Bristol Composite Institute. Thank you to everybody attending this workshop. Hassam has shown results related to different types of coated and compounded rubber sheets. I would say that really the dimensions are really lab scale, small scale. The results that I will show here are related to the large scale compounded rubber paddles for construction applications. And we are talking about rubber panels that are made without lignin reinforcement, up to 20% of weight fraction of lignin reinforcement. To assess the performance of these types of panels, we have designed in Bristol a flexible platform or reconfigurable platform to host the panels at different heights, and also to perform different types of ISO standard test using impact, sine wave, electrodynamic shaker, but also walking test. And in terms of tests with hammer and sine sweep, we have a look at the frequency range between 0.5 and 30 Hz, which is typical of floor vibration in most of the available buildings. We have also considered the presence of concentrated masses of equivalent to 75 kilograms to consider the static presence of persons already sitting on those panels. But we also performed a walking test. Walking test made really by human operators, or 70 kilograms of average weight plus bag. Please the next. And the tests have been carried out on these two types of panels. And the data that you see over there are related to sine sweep test, and you can appreciate from the graphs really the sort of the difference in terms of response provided, but when we use only the actuator on the stiff platform, which has got 3 meters span length, and a flexible platform, 5 meters span length. All the data have been filtered using a third order pass filter, so we could cut out really the frequencies between 0.5 and 20 Hz. Again, those are representative frequencies in floor vibration. Next, please. Just to give really a sort of summary of the results, when you look at those tables of type 1 tile, that corresponds to the test made with the panels with 0% of lignin, while the type 2 are 20% with fractional lignin. As you can see, you have the comparison between the bare system, so we have no panels, and then the presence really of the two panels. there is a more sort of significant increase of damping with the presence of the rubber panels, especially when we are looking at the more flexible configuration, so the 5 meters of span length. And if you remember, as Ams talked before, he was already mentioning, depending very much really on the type of application, really compliance is one of the strong points of this type of rubber solution. The same, something similar can be also be seen when we put really a static mass of 75 kilograms representing a person on top of really other two rigid and flexible platform. In the case, you can see that there is an increase in damping, especially on the more flexible configuration. However, if you look really at the specific figures, we are talking about some sort of marginal increases. And what is not noticeable that, especially for when we have the presence of the mass, we always have a sort of a decrease of the resonant frequency of the base platform as soon as we put the mass and the panels. Next, please. Some more interesting results have been measured when we consider really large-scale working tests. So these are the typical spectra of a large-scale test. So we measure really the peak acceleration and also really the displacement test history from the sensor on the platforms. And we average, calculate really root mean square average and standard deviation so we can compare the different configuration. Next, please. If you look really at the stiff platform, so there is already a tangible effect when we consider the presence of the panels and also the presence of the rubber with the lignin. You can see that there is a sort of an attenuation of the peak acceleration. Also in terms really of displacement, you have an attenuation. More interesting results appear when we consider a flexible platform this step around. And Tom, if you can click over once again. I just want to draw your attention to on the flexible platform to the significant increase of the attenuation of the response really of the system when we put really the two classes of rubber panels, and both in terms of attenuation, but also when we put we consider also really the standard deviation for the displacement. So over there is some indication that effectively, not only the rubber panels provide an attenuation, consistent attenuation to the response when people are walking on top, but also the presence of the lignin provides an added damping. And at the same time, it also added sort of stiffening because the peak displacement are reduced. So the lignin here appears with these types of walking type of loading to provide some sort of local slipstick really friction type of dissipation that actually not only provide an increased damping but also an increased stiffness. And these results are, I think, really are quite interesting. They're all based on ISO standards, and I think they could be quite meaningful really to think about the importance of design of floor boards using these types of materials. Next, please. What I will show here are some results related to one of the applications related to the sort of the circular economy. So we devulcanize the rubber, so we recycle the rubber, we make the panels, we use the panels, and then we need to recycle the panel. So the recycling can be done by granulating again, for example, the panels. So this is a strategy. So when we talk about granules and particles, there is a sort of a niche application that may be quite interesting, and these are the particle dampers. Particle dampers are passive devices that use the interaction of particles within a confined space to damp a vibration. So there is a transfer of momentum between the heats between particles and the constrained volume of the container. Then there are also really tangential friction effects. Effect of fluidization is a little bit what happens in earthquake when you start really to fluidize really the soil, the sand at specific frequencies. Those are nonlinear dampers, but actually they are quite effective. They are used in civil construction at the base, for example, really of very tall towers, but they are also used inside turbine blades, rocket engine, turbopumps, and rotary printing equipment. And just to give you an idea how they work, Tom, if you could click already on the video, please. This is a particular type of particle damper with ABS plastic beads. Other types of commercial particle dampers, they have steel or glass beads inside. But you can see that really during the motion, during the vibration, there is this transfer of momentum and different types of sort of hits and impacts between the particles and the volume of the container. Next, please. I'm really sorry for the equation that you will see in the slide. Unfortunately, we need sometimes we need those. So you imagine that you have a sinusoidal type of excitation given by the sinus function, and you can quantify a sort of normalized, the really maximum amplitude displacement based on the acceleration and the displacement imposed. This is tau. We then define an efficiency of the energy dissipated by the damper, this epsilon granular. The measure, the dissipated energy actually is quite difficult to measure. You need to couple really the vibration testing rig with a high-speed camera and calculate really the velocities and equivalent impact forces for the different particles. But the maximum energy dissipated is a function of the number of particles and is theoretical. What is very important is how you punch dissipated energy, granular, per weight. So in other words, Tom, if you can click on the video over there, the granular damper that you see over there is the one made with recycled rubber particles. They are roughly over 2.5 millimeter of diameter, and has got the same volume fraction of the previous damper that I showed you before. Now, already the behavior of the two is quite different, and the particle dampers with rubber actually provides a better sort of elastic response and creates also better visual fluidization, especially at low frequencies. If you can go to the next slide. In this slide, you see what happens when you excite a low frequency vibration, the damper. You can see the efficiency versus the sort of the normalized excitation, maximum excitation tau. Well, low frequency vibration are between the most difficult ones really to damp with normal types of materials. If you compare a classical particle damper made really with the ABS plastics and the one with the rubber, you will see that a low frequency vibration, the rubber provides a better elastic response, better fluidization, so you have a higher efficiency per unit weight because the rubber, even though it has got the same volume fraction that the ABS, is lighter. When you increase the vibration, the situation is slightly different. These are sort of particle dampers with highly nonlinear type of behavior. At the moment, we are exploring also other types of volume fraction. But the fact that, Tom, just really to give a little bit more emphasis on this message, the fact that we can really witness increased energy dissipation efficiency, lower frequency, high vibration amplitude, this is something very important and very notable within the vibration damping community. Again, those are particles obtained from recycling the overall panels that we have made. And with this, already I finish my talk. I give back early the stage to Tom.
That's great. Thank you very much, Fabrizio. So now we're going to move on and look at another functional property, really. So it's the reaction to fire results that Frédéric Nez is going to talk about. So he's from ZAG, who are based out in Slovenia. So Frédéric, I will pass it over to you.
Yes, thank you. Thank you very much. First, apologies for not seeing me on my camera. Unfortunately, some technical issues there are present, but I hope you will still get the message. Please, next slide. Yeah. So first, let's discuss just a little bit about fire. This is important because it's not very well known, but in principle, we differentiate two sets of characteristics. One is reaction to fire, and the other one is fire resistance. We're not going to talk about fire resistance. This is property of a structure. We're going to talk about reaction to fire. Now, reaction to fire is fairly or highly regulated property within the construction sector across Europe, and we all more or less base characterization and the results and the properties of materials in the so-called Euro classes, or in the classes of reaction to fire, where we have classes A1 and A2 for non-combustible material, classes B and C for hardly combustible material, classes D and E for flammable materials, and there's also class F for other materials that would basically be fuels. When we are testing reaction to fire, what we're trying to assess is actually what happens with the surface of the product and the product lying behind the surface, the active surface, if it is exposed to fire. There's obviously various situations. So non-combustible materials withstand any fire down to the class E, which are safe for small fires when they originate. When they start the process. Here are some general pictures of the materials, and you can see the rubber or the tires, better to say, are expected to be in class E because these are polymers, these are combustible polymers. So it is not possible to do miracles based on this material, but nonetheless, there are some possibilities as we will show. Next slide, please. So when we start measuring fire and fire properties, we first start with a cone calorimeter and the heat release rate. So here we have certain curves. What we see on these curves is that the black, so the lower the heat flux incident, the longer it takes to ignite. We can see that rubber without lignin, for example, ignited in approximately 700 seconds, whereas in 15 kilowatts, and at about 2 minutes in 25 kilowatts per square meters. And when we are adding lignin, we are actually making the ignition faster. But what we're also making is we're making the heat release rate less, so to say, violent, or less, so to say, less intensive. So it's more spread. Initially, one would expect that lignin, being agent for intumescence, would strongly improve reaction to fire properties of material, but this is actually not the case because the lignin as such still burns, and intumescence helps if it is applied to the outer side. We'll see that in the last slide, but not in any application of the material of the lignin into the material. Yeah, so I've commented this. Next slide, please. The first test that we normally do with material that we expect not to be non-combustible is the small flame test. This is a standardized test. And on the left, you can see the attack on the sample. So in the middle, here in the middle is sample, and the attack with flame. And the exposure is either 15 or 30 seconds. It depends on what are our targets. And then we observe whether the material has ignited and whether the progressing of fire was big or not, so to say, and when the ignition or not the ignition, but the combustion stopped. So for Class E requirements, it's 15 seconds pilot flame, and for Class D, C, or B, so the higher classes, it is 30 seconds pilot flame exposure. The results that we have obtained on these materials are showing that actually small flame test in these materials is fairly good. It's complying to the Class D, C, or B, not only Class E, which is to give you a comparison, which is better than expanded polystyrene or extruded polystyrene or some other foam material that is typically used for insulation materials or being used on the facade as well. Next slide, please. Once we have this behavior, we continue with larger tests. This is the so-called single burning item. This is the real test or the full test for assessing whether we comply to the Class D or C. We have done that. Unfortunately, we found out that we are missing the criteria for Class D, so we are actually in Class E. Now, what does it mean in practice? It doesn't mean a lot, because neither Class E or Class D are materials that can be just left on the wall or somewhere to be exposed to fire because they will ignite. This leads us to the first, let's say, characterization, saying that we have good Class E, but we unfortunately do not have Class D. So the Class E is realistic for untreated materials, requires either covering or additional surface treatment, which we'll see in the aftermath of the presentation. Next slide, please. Yeah, then we've done the same test on flooring, so on horizontal spacing, and the result is actually very similar. You can see here a device. We have here variable heat flux depending on the density. So the fire propagated not very fast, but still too fast to reach Class D. So we also have Class C in flooring for reaction to fire on that application. Next slide, please. And then, of course, we were looking at what we can do. And we have selected three types of, let's say, fire retardancy or surface treatment that could actually help a lot in reaction to fire properties. So we first said, okay, let's use a commercial one that is available and apply it. The second one is use water glass or sodium silicate. And the third solution was use water glass, but also add some lignin inside to the surface. What we found out is that the commercial material did not work with rubber very well, and actually did not stick at all on the material. So it's impractical. However, water glass, known to be good fire retardant, was already adhering to the surface, but when adding lignin, and we were able actually to add only 1% of lignin by weight, made the adhesion much better. So this seems clearly to be the way of treatment of the surface in order to enhance fire performance significantly. And what we have for the result, next slide, please. So what we see here is, if we look at the three pictures, on the left side is with no treatment. You can see the intumescent, so the swelling effect of the rubber, but it is still burning. Whereas if it is covered with water glass, there is still swelling, but there is no burning. This is very nicely shown on the charts, where we can see on the lower part there was no ignition. So treatment with water glass or that sort of treatment of the surfaces may truly make the results or the reaction to fire much higher. Obviously not in class A, because it is still combustible. There is still heat flux in which the material would ignite, but it is really improving the results. So this is actually a little bit work in the development. We're not finished with that entirely, but it is quite promising direction on, let's say, modification or addition to the rubber boards in order to get a much more favorable reaction to fire results. I will not go into details about which one ignites sooner, which one ignites later, but basically what we see is that clear or pure addition of lignin actually worsens the reaction to fire. But if we add it on the right places, we can maintain both mechanical and vibrational characteristics, as Fabrizio was saying before, but also not risk reaction to fire. One thing I also like to add: the application that Fabrizio has shown in the end is not critical at all for fire, because it's not exposed, so it's really viable direction, not contemplated in the very beginning of the project, but this is why the projects are interesting, because the path of application may lead you to some directions which were not foreseen at the beginning. So next slide, please. I think, yeah. The last thing we have checked is when we actually burn the materials, when the ignition occurs, what happens what happens with the gases, because toxic gases are often of high concern in fire. And here we have charts. Obviously, where we had no ignition, the toxic gases emitted are very close to zero. What you see on the right chart are percentages of the limit values. In a nutshell, all the critical gases, the SO2, the sulfur, SO2 gas is the one that is let's say toxic. It is an irritant and is present in combustion gases, but it reaches approximately up to 55% at the maximum of the limit value. So what we can conclude out of this analysis is that no gas, so the combustion gases and of these materials are not toxic, at least not to the extent that would exceed the limits, and are not harmful. Maybe unpleasant, obviously, but not harmful. So here we have 7 gases, but actually we tested for 22 gases. These are the exposed results, because these were those that were actually seen on FTIR. The others were even less than virtually not detected. And the criteria taken into account here is the criteria for shipbuilding industry, which is a little bit more stringent than one would expect for buildings. The reason why we don't use limit values for buildings is that they mainly don't exist, or they very, very rarely exist on the ships. The ships, it is completely a different story. So, but even for ships, it would be okay with respect to gases. So next slide, please. I think we're at the end. Yes. Thank you very much. Thank you for listening, and I suppose back to you, Tom.
Grand. Thank you very much, Frederic. So just to wrap up then and conclude, so what we've talked you through today really is the journey we've been on, I suppose, from very small scale formulation. We started off producing composites that were 60 grams in mass. We've scaled that up now, so we've produced about 100 kilos of material in total, and we're now manufacturing 0.5 meter by 0.5 meter panels. So that's both the uncoated panels with and without lignin, then the coated panels, and then as Sam talked about, some of these multi-layer coated panels. That's allowed us to scale up really this kind of testing we can do to get to some realistic real world testing. So the acoustic and vibrational testing that Fabrizio talked about, and then the fire testing that Frederic has just run you through, and some really promising results there on the vibrational side, and also particularly for the coated panels for the reaction to fire testing. So thank you very much for listening. Thank you very much to speakers, because we've kept almost exactly to time, which means we've got about 10 minutes for any questions that anyone on the call has. I'd ask, if you do have questions, if you could just raise your hand on the Teams meeting, and we can come to you. So over to you guys, really. Yes, Vicente, go ahead.
Thank you, Tom. Thank you very much. A nice presentation of all the speakers. My question is for a Zach presentation regarding to the use of lignin. Results respect to the flame retardant, and more specifically respect to the use of lignin. I'm not sure if you did you use crude lignin or native lignin, or you were using a fraction of lignin. In case of not, if you can consider if it is possible to enhance and to increase the behavior of a flame retardant if you use a fraction of lignin in low molecular weight space in order to improve the capacity to the flame retardant, and also it is necessary to remove the sulfur content in order to reduce the toxic gases, more referring to the oxide of sulfur, for example.
Yes, thank you for the question. So with respect to the type of the lignin, that is actually more question for the NCC, because the way I understand the source is from biomass, and it is done with treatment. What we have seen is actually that addition of lignin, because it is still combustible, and I don't think this would change much based on type of the lignin, actually does not help, because intumescence is not the mechanism that one would want here. You would have to use other mechanisms like cooling of the sample, or reducing the oxygen excess, but intumescence or charring of the surfaces is typically reserved for surfaces, which is actually what happened with water glass. And as for removing the sulfur, obviously yes, the more you remove sulfur, less SO2 you will get, but we are at worst case, we are at 50% of the limit that is deemed to be harmless. So I don't think there is any need for further reduction. But obviously, if we reduce, if we remove sulfur even further, or if we remove sulfur, it will create lower SO2 creation.
Thanks, Frederic. And just to come in behind that, yeah, so it's craft lignin that we were looking at, and without any fractionation or chemical modification. So yeah, it's a very good point, and that would certainly be a potential next step to see how we could increase the impact of that lignin on the fire retardancy. Thank you. Any other questions from the floor? No? Okay. Was that someone there? If not, No, it doesn't sound like it. In which case, thank you all very much for listening. Really appreciate your time, and thank you very much to all the speakers today. Rita, I don't know if there's anything else you would like to say to wrap up the meeting today.
Of course, I want to thank you all for attending, and also for the speakers for the insightful information and presentation. If I can now share my screen to share the evaluation survey QR code. Thank you, Tom. This won't take more than a couple minutes to fill out. It's just for us to have a feedback on your perception of this session. So I'll give you a couple minutes to fill it out, and then we can all leave the meeting. Thank you all. All right. Once again, thank you all for attending. I hope you have a nice day. Goodbye.
Goodbye.
Thank you for the presentations. Have a nice day.
Bye-bye.
Thank you.
Bye.
Bye.
Thank you.
Bye.